Graduation Cap KAYHAB 17, HSE Global Safety Leader Professional Training Academy. Module 10, Advanced Permit to Work in High-Risk Operations. Professional Level, Advanced HSE Construction Oil and Gas Petrochemical LNG Refinery. Module Introduction. Wide cinematic shot of a refinery expansion project. 4 activities are taking place in the same general work area. Welding on a pipe, spool, crane, lifting equipment, excavation for underground services. Workers preparing for vessel entry. Show 4 separate permit boards appearing on screen. Everything initially appears controlled. Then gradually highlight the interfaces between the activities. A crane load moves near the excavation. Welding sparks appear close to a process area. A vessel entry team prepares to enter. A warning symbol appears between the permits. This module takes us beyond basic hazard identification. We are moving into the area where safety management becomes a question of authorization, coordination, verification, isolation, communication, and professional decision-making. Let us begin with a realistic situation. Imagine a refinery expansion project. A welding crew has an approved hot work permit. A maintenance team has a permit for vessel entry. A crane team has authorization for a lifting operation. And another contractor has an excavation permit. Now I want you to think carefully. Each permit may have been properly prepared. Each risk assessment may have been completed. Each supervisor may have signed. So here is a professional question. Are the 4 permits still safe when they interact with one another? That is the heart of this module. A permit can be individually acceptable, and yet the combined operation can create an unacceptable risk. The crane may affect the excavation. The hot work may affect the vessel entry atmosphere. The excavation may affect underground services. The movement of people, vehicles, and equipment may interfere with emergency access. And a change in one activity may invalidate the assumptions made in another. This is why advanced permit to work management is not about paperwork. It is about controlling work in the real operating environment. HSE guidance describes PTW as a formal system specifying what work is to be done, when it is to be done, which parts of the plant are safe, and who is responsible. It also emphasizes that the permit itself does not make the work safe and that related permits and simultaneous activities need to be coordinated. HSE. So throughout this module, remember one principle. A permit does not authorize risk-taking. It authorizes controlled work under defined conditions. Learning objectives. By the end of this module, you should be able to, first, explain the purpose and principles of a permit-to-work system. Second, identify common permits used for high-risk activities. Third, understand the relationship between risk assessment, method statements, JSA, and PTW. Fourth, explain gas testing requirements and limitations. Fifth, understand isolation certificates and energy isolation. Sixth, explain when a permit must be suspended. Seventh, understand permit handover, extension, revalidation, and closeout. Eighth, identify interactions between simultaneous operations. Ninth, verify permit controls at the actual work location. And 10th, apply these principles to realistic high-risk industrial scenarios. This module is designed to develop professional judgment, not simply the ability to complete a form. Lesson 1. Permit to Work System. 1. What is a permit to work? Permit form appears. The form transforms into a field scene. Show the words, scope, hazards, controls, authorization, verification, communication. Let us start with the foundation. What is a permit to work? A permit to work system is a formal process of controlling specified hazardous or non-routine work. It defines what work will be performed, where it will be performed, when it may be performed, who is authorized to perform it, what hazards are present, what controls are required, what isolations are necessary, what conditions must remain in place, and importantly, when the authorization is no longer valid. A good permit therefore establishes a control boundary around the work. But here is a critical distinction. A permit is not a magic safety document. Signing a permit does not remove the hazard. HSE guidance explicitly emphasizes that issuing a permit does not, by itself, make a job safe. The permit functions as part of a wider safe system of work and helps bring the risk assessment into practical field execution. HSE. Think of it this way. The risk assessment asks, what can harm people, property, process, or environment? The method statement asks, how will the work be performed? The JSA asks, what can go wrong at each task step and what controls are required? The permit to work system asks, under what defined conditions is this work authorized to proceed? And field verification asks, are those conditions actually present here and now? That creates a control chain. Risk assessment. Method statement. JSA our task risk assessment. Permit to work. Field verification. Safe execution. Monitoring. Closeout. This relationship is extremely important. A permit should not become a substitute for proper risk assessment. Similarly, a risk assessment should not remain a document sitting in an office. The controls have to reach the point where the work is being performed. 2. Core principles of PTW. 6-stage animated process. Plan, authorize, verify, execute, monitor, close. A mature permit-to-work system follows a logical sequence. Plan before execution. Understand the work. Identify hazards. Determine controls. Confirm competence. Determine required permits and isolations. Then authorize. But authorization is not the end. Before work starts, verify. Is the correct equipment being worked on? Is the location correct? Are the isolations installed? Has gas testing been completed where required? Are barricades established? Are emergency arrangements available? Are the workers briefed? Are simultaneous activities controlled? Only then should execution begin. During execution, monitor, because conditions can change. Weather can change. Process conditions can change. Personnel can change. The work scope can change. Equipment can fail. Another contractor can start work nearby, and therefore the permit may need to be suspended or revalidated. Finally, close the work properly. The work site must be inspected. The plant or equipment must be returned to an appropriate safe condition. The permit must be formally closed in accordance with site procedure. This is why PTW is a management control loop, not simply a document. 3. Typical high-risk permits. Permit board displaying. Hot work confined space excavation electrical or isolation line breaking work. At height cold work radiographer lifting related authorization. Permit categories vary between companies and jurisdictions. A site may have hot work permits, cold work permits, confined space entry permits, excavation permits, electrical or isolation permits, line breaking or breaking containment permits, work at height authorization, radiography controls, and specific lifting or critical lift controls. The important point is not memorizing the names. The important point is understanding which work requires formal authorization under this organization system, and what conditions must exist before that authorization is valid. Lesson 2. Hot work permit. Welder preparing a pipe spool in refinery. Display. Ignition source plus flammable atmosphere plus fuel equals fire explosion potential. Now let us move to one of the most recognizable high-risk activities. Hot work. Hot work includes activities capable of producing sufficient heat, sparks, flame, or ignition energy to create a fire or explosion hazard. Examples include welding, cutting, grinding, brazing, gouging, and other spark or flame-producing activities. In an operating hydrocarbon environment, hot work must never be treated as simply put on PPE and start welding. The professional question is, what could ignite and what could be ignited? Before authorizing hot work, the team should consider the work location, nearby hydrocarbons, potential vapor sources, drains, openings, adjacent equipment, piping, vessels, combustible materials, wind direction, ventilation, nearby simultaneous operations, and the potential movement of sparks or hot particles. Gas testing for hot work. Competent gas tester performing atmospheric test. Display 4 indicators. O. Flammable atmosphere, toxic gases, trend. Gas testing is a critical control where required by the risk assessment and site procedure. But gas testing must be understood correctly. A gas test result is a measurement at a particular time and location under particular conditions. It is not a permanent guarantee. For example, suppose the atmosphere is acceptable at 8 o'clock. At 10 o'clock, a process valve changes condition. A hydrocarbon release occurs nearby. wind direction changes, ventilation fails, or another operation changes the atmosphere. Is the 8 o'clock reading still sufficient? Not automatically. This is why monitoring requirements must be defined according to the task, risk assessment, and site procedure. Consider instrument suitability, calibration status, bump testing where required, sampling technique, sampling location, low and high areas where relevant, potential pockets, test frequency, continuous monitoring where required, alarm response documentation. Do not invent universal gas test limits. Acceptable concentrations and alarm settings must follow applicable law, process information, equipment requirements, site procedures, and approved permit criteria. This is an important professional principle. Use the applicable standard. Do not manufacture a number because someone expects an answer. Fire watch and hot work controls. Fire watch position with extinguisher. Spark containment screen installed. Nearby drains covered where appropriate. Barricade established. Narrator. Hot work controls may include a trained fire watch, suitable fire extinguishing equipment, removal or protection of combustible materials, spark containment, control of openings and drains where appropriate, barricading, inspection of adjacent areas, appropriate welding equipment, correct cable condition, effective grounding, emergency communication, and define post-work monitoring where required. The fire watch is not simply somebody standing nearby holding an extinguisher. The fire watch must understand the hazards, know the area, understand the alarm and emergency arrangements, maintain appropriate observation, and have the authority to raise concerns and stop the activity in accordance with site arrangements. Now consider this question. The permit says hot work is approved. The gas test was acceptable, but the fire watch has left the area. Would you continue? No. The permit controls are no longer fully implemented. The correct response is to pause the activity and restore the required controls before continuing. That is professional permit management. Lesson 3. Confined space entry. Large process vessel with entry manway. Show attendant outside, gas detector, ventilation, rescue equipment, and entrant. Now we move to another high-risk operation. Confined space entry. A confined space is not simply a small room. The classification depends on the characteristics of the space and the reasonably foreseeable risks. These can include fire, explosion, loss of consciousness, asphyxiation, drowning, toxic atmospheres, oxygen deficiency, engulfment, mechanical hazards, flooding, and other serious hazards. HSE guidance emphasizes avoiding entry where reasonably practicable. Where entry cannot be avoided, the work requires appropriate risk assessment, precautions, and emergency arrangements. HSE. So the first question should be, can the task be completed without entering? If yes, that may eliminate the entry risk. If entry is necessary, then a comprehensive safe system of work is required. Confined space control system. Assess, isolate, test, ventilate, authorize, enter, monitor, rescue, ready, exit, close. Before entry, establish the scope of work, the hazards, the isolation requirements, atmospheric testing, ventilation, entry arrangements, attendant requirements, communication, personal protective equipment, emergency arrangements, rescue arrangements, and permit validity. The atmosphere must be assessed according to the hazards identified. This may involve oxygen, flammable gases or vapors, toxic contaminants, and other atmospheric hazards relevant to the specific space. Testing should be conducted using suitable equipment and appropriate sampling methods. And remember, a confined space can change. It may be safe at one moment and unsafe later. A valve can leak. Ventilation can stop. A process connection can introduce gas. A welding operation can consume oxygen or generate hazardous fumes. A person can become incapacitated. Therefore, atmospheric monitoring must reflect the risk. Rescue team preparing tripod retrieval equipment. One of the most dangerous mistakes in confined space work is treating rescue as an afterthought. A rescue plan must exist before entry. The question is not, who do we call if something happens? The professional question is, exactly how will we recover the person from this space? Who raises the alarm? Who controls the entry? Who initiates a rescue? What equipment is required? Can the casualty be retrieved vertically? Is respiratory protection required? Can the rescue team safely enter? What happens if the entrance collapses near the bottom? What happens if the emergency involves fire or toxic gas? HSE guidance specifically emphasizes that confined space emergency arrangements should not simply depend on an external emergency service arriving after the event. HSE, the rescue capability must therefore be proportionate to the credible emergency scenarios. And one more principle. Never create a second casualty by sending an unprotected person into a hazardous atmosphere to rescue the first. Lesson 4. Isolation and LOTO. Pump with electrical, mechanical, hydraulic, and process energy sources. Animated energy arrows gradually disappear. We now reach one of the most technically critical elements of high-risk work. Isolation and energy control. Let us establish one principle immediately. Switching equipment off is not the same as isolating it. A machine can be switched off while energy remains available. A pump may stop operating while electrical energy remains connected. A hydraulic system may be shut down while pressure remains trapped. A vessel may be disconnected from one source while another source remains connected. A suspended load can contain gravitational energy. A spring can contain stored mechanical energy. A capacitor can retain electrical energy. A process line can contain pressure or hazardous material. Therefore, the isolation process must consider all relevant energy sources. The isolation sequence. Large animated sequence. Identify. Isolate. Lock. Tag. Dissipate, control stored energy. Verify zero energy. Perform work. Restore safely. Start by identifying every hazardous energy source. Electrical, mechanical, hydraulic, pneumatic, pressure, thermal, chemical, gravity, stored energy. Then establish the required isolation points. Install the required locks and tags according to the organization's LOTO procedure. Control stored energy. Drain, vent, depressurize, discharge, block, secure, or otherwise control the energy as required. Then comes one of the most important stages, verification. You do not simply assume that isolation has worked. You verify. Try the equipment where the procedure permits. Test electrical absence using the approved method. Confirm pressure has been released. Confirm the correct valve positions. Confirm the correct equipment identity. Confirm the isolation boundary. The precise verification method must follow the approved site procedure and equipment requirements. Isolation certificate. Isolation certificate linked visually to permit. In many process industries, the isolation certificate is an important interface between operations and maintenance. The permit says, this work is authorized under these conditions. The isolation certificate says, in effect, these specified energy or process sources have been isolated under the defined isolation arrangement. The two systems must therefore interact. HSE's HSG 253 guidance specifically addresses the interface between isolation arrangements and work control systems such as permit to work. It also emphasizes accurate plant information, verification of isolations, and safe reinstatement. HSE. Consider a maintenance task on a process pump. The worker believes a pump is isolated, but the wrong pump was identified. The electrical breaker is locked. However, a parallel process line remains pressurized. The work begins. What failed? Not simply the worker. The isolation system failed at multiple levels. Identification, isolation, verification, communication, and supervision. This is why effective isolation is a system, not merely a padlock. Lesson 5. SimOps Management. 4 activities appear. Fire hot work. Building construction #crane lift. Pick #excavation. Oil drum #vessel entry. Lines connect each activity. Some lines turn red to indicate conflicts. Now we reach one of the most important concepts in advanced permit-to-work management. SimOps, simultaneous operations. SimOps means that different activities are occurring at the same time and may interact. The danger is that each work team may focus only on its own task. The welding supervisor thinks about welding. The crane supervisor thinks about lifting. The excavation supervisor thinks about the trench. The vessel entry supervisor thinks about the entrance, but the HSE professional must think about the whole system. SimOps scenario. Imagine the following. A welding crew is preparing to weld a pipe spool. At the same time, a crane is lifting equipment. Approximately 20 meters away, another contractor is excavating, and inside a nearby vessel, workers are conducting an inspection. 4 permits, 4 supervisors, 4 risk assessments, but 1 work environment. Now ask, can these activities interact? Absolutely. The crane may affect the excavation through ground loading or exclusion zone conflict. The lifted load may pass near people or equipment. Hot work may introduce ignition energy into an area where flammable vapors could migrate. The vessel entry team may depend on emergency access that becomes obstructed by the lifting operation. The excavation may interfere with emergency routes. A contractor may unknowingly enter another team's exclusion zone. Therefore, the PTW system must control the interfaces. Permit interaction. Permit board with connecting arrows. Activity. Interaction. Control. Welding. Vessel entry. Atmosphere ignition control. Crane lifting. Excavation. Ground stability or exclusion zone. Excavation. Underground services. Service identification isolation. Vessel entry. Nearby hot work. Atmosphere emergency response. Electrical maintenance. Mechanical work. Energy isolation. Multiple contractors. Shared area. Coordination communication. This gives us a powerful question. How does my permit affect everyone else's permit? That question should become part of professional HSE thinking. HSE guidance specifically identifies PTW as a means of coordinating different work activities and recommends linking related permits and considering simultaneous or interdependent activities. HSE. This is where SimOps matrix becomes useful. It can identify compatible activities, activities requiring additional controls, activities requiring separation, and activities that should not proceed simultaneously. The exact rules must come from the site's PTW and SimOps procedure. There is no universal matrix that can simply be copied from one facility to another. Permit interaction, professional decision. HSE officer reviewing 4 permits. Now consider this question. Which permit takes priority? There is no universal answer that says, for example, the hot work permit always wins. Instead, the work should be assessed through the site's permit hierarchy, area authority arrangements, risk assessment, operational requirements, and SimOps controls. The correct question is, can all activities be conducted simultaneously without creating unacceptable combined risk? If not, one or more activities must be rescheduled, separated, modified. Additional controls must be introduced, or the work must not proceed simultaneously. That is SimOps management. Gas testing, advanced application. Gas detector connected visually to hot work and vessel entry permits. Let's return briefly to gas testing because it affects several permit categories. Gas testing is not simply test, right number, sign permit. A competent gas testing process considers what hazards are expected, where can the gas accumulate, what is the ventilation pattern, where should samples be taken, what equipment is appropriate, how frequently should testing occur, is continuous monitoring necessary, what happens if the detector alarms, who has authority to stop the work, what happens after an alarm, and has the atmosphere returned to an acceptable condition according to the applicable procedure before work is reconsidered. This is why atmospheric monitoring must be connected to decision-making. A detector is not a safety system unless people respond correctly to what it tells them. Permit suspension. Active permit turns from green to amber to red. Now we come to one of the most important responsibilities of an HSE professional, knowing when to stop. A permit may need to be suspended when weather deteriorates, gas test results become unacceptable, an alarm activates, an isolation is compromised, equipment fails, the work scope changes, a new hazard appears, a SimOps conflict develops, communication is lost, an emergency occurs, and an authorized person enters the work zone, process conditions change, an excavation becomes unstable, a hydrocarbon release occurs, or the permit expires. Consider this scenario. A crane lift is underway. The wind begins to increase. The load starts moving unpredictably. The project manager says, "We are already late. Let's finish quickly." The HSE officer says, "Stop. Is that an obstruction to production?" No, it is risk control. Stopping work is not a failure of the safety system. Sometimes failure to stop is a failure. The safe suspension process. 8-step flowchart. Recognize, stop, inform, reassess, verify controls, update, communicate, restart. When conditions change. Recognize a change. Pause or stop the work. Inform the responsible personnel. Reassess the risk. Verify the controls. Update the relevant documents and permit arrangements. Communicate the change to everyone affected. Then, restart only when the responsible authority confirms that the conditions for safe work have been restored. This connects directly with professional risk management. NEBOSH's current general certificate places risk assessment, control, and workplace application at the center of the qualification. Its current materials also emphasize applying knowledge to real workplace situations rather than treating safety as purely theoretical. NEBOSH, practical field verification. HSE officer walks from permit office to actual worksite. Split screen. Paper approval versus field verification. Here is one of the most important principles in this entire module. Paper approval is not field verification. An HSE professional should not be satisfied simply because the permit contains signatures. Go to the worksite. Verify the actual location. Verify the equipment. Verify the work scope. Verify personnel. Verify competence. Verify PP. Verify isolations. Verify gas testing. Verify barricades. Verify fire protection. Verify rescue arrangements. Verify JSA. Verify the method statement. Verify the toolbox talk. Verify permit validity. And most importantly, verify that the controls described on paper exist physically in the field. This is where safety documentation becomes operational control. Practical SIMOPS exercise. Full screen exercise scenario. Refinery expansion project. 4 activities. Hot work. Crane lifting, excavation, vessel entry. Now it is your turn. Imagine you are the HSE professional responsible for reviewing the day's high-risk activities. The refinery expansion project plans to conduct 4 activities simultaneously. Activity 1. Hot work on a pipe spool. Activity 2. Crane lifting of equipment. Activity 3. Excavation for underground services. Activity 4. Vessel entry for internal inspection. Before you authorize the work, answer these questions. Question 1. Which permits are required? Do not assume the answer is identical on every site. Check the site's PTW procedure and permit matrix. Question 2. What hazards exist? Consider fire, explosion, atmosphere, dropped objects, crane stability, excavation collapse, underground services, energy sources, confined space hazards, vehicle movement, emergency access, personnel interaction. Question 3. What isolations are required? Identify electrical, mechanical, hydraulic, pneumatic, pressure, process, and other relevant energy sources. Question 4. Where is gas testing required? Consider hot work, vessel entry, potential hydrocarbon release, process conditions, and any other atmospheric hazards identified by the risk assessment. Question 5. What activities conflict? Look for interactions. Does a crane operation affect the excavation? Does hot work affect vessel entry? Does vessel entry depend upon emergency access? Does excavation interfere with crane access? Question 6. What exclusion zones are required? Define boundaries based on the actual hazards and site procedure. Question 7. What emergency arrangements are required? Think about fire, confined space rescue, drop loads, excavation collapse, hydrocarbon release, medical emergency, evacuation, muster, communication. Question 8. Who can stop the work? A mature safety system should provide appropriate authority for workers and supervisors to raise concerns and stop or pause work when unsafe conditions exist, consistent with organizational procedures. Question 9. What would require permit suspension? Changing weather, failed gas test, loss of isolation, equipment failure, change in scope, SIMOPS conflict, emergency, loss of communication, or any other condition that invalidates the permit assumptions. Question 10. What must be verified before restart? The hazard, the revised risk, the controls, the permit, the isolation, the worksite, the personnel, the communication, and the authorization to restart. Model professional answer. Answers appear one by one with green verification marks. The professional answer is not, check the permits and let them start. The professional answer is, control the interfaces. First, identify all applicable permits. Second, review their risk assessments and supporting documents. Third, identify common hazards. Fourth, identify conflicting activities. Fifth, confirm isolation requirements. Sixth, establish exclusion and controlled zones. Seventh, verify gas testing requirements. Eighth, confirm emergency arrangements. Ninth, conduct field verification. 10th, communicate the SIMOPS controls to all affected teams. Then authorize only those activities that can safely coexist. If they cannot safely coexist, change the sequence. Safe scheduling is itself a risk control. Case Study 1. Hot work. Welding activity beside refinery process equipment. Case Study 1. A welding crew receives a hot work permit. The initial gas test is acceptable. The area is barricaded. A fire watch is present. The welding begins. 30 minutes later, the gas detector begins to alarm. What should happen? The answer is simple. Stop the hot work. Do not argue with the detector. Do not continue because the permit has already been signed. Do not say, we tested earlier. The current condition has changed. The work must be stopped and the cause investigated according to the site's procedure. The atmosphere must be reassessed. The source of the change must be identified. Controls must be restored or modified, and the work must not restart until the responsible authority determines that the conditions are acceptable. Lesson. A permit controls conditions, not just activities. Case Study 2. Confined space. Vessel entry. Gas monitor changes from green to alarm. Case Study 2. 3 workers enter a vessel after atmospheric testing. The initial atmosphere is acceptable. 30 minutes later, ventilation fails. The gas detector alarms. 1 worker reports dizziness. What should happen? The entry must be stopped. The emergency arrangements must be activated as appropriate. The attendant must raise the alarm. Personnel must not enter the vessel impulsively to rescue the casualty unless they are trained, equipped, and authorized to do so under the rescue plan. The rescue must be performed according to the established emergency arrangements. HSE guidance emphasizes that confined space rescue arrangements should be established before work starts and should be appropriate to the foreseeable emergency. HSE. Lesson. The permit should anticipate the emergency before the emergency occurs. Case Study 3. SIMOPS. Crane, excavation, welding, and vessel entry shown simultaneously. Case Study 3. A crane is lifting equipment near an excavation. At the same time, welding is taking place nearby. Workers are inside a vessel. All permits are approved. Then the crane supervisor requests that the exclusion zone be expanded. The expanded zone now obstructs the vessel entry emergency route. What happens? The lifting permit cannot simply continue because it was approved earlier. The vessel entry team must be informed. The SIMOPS arrangement must be reassessed. The emergency route must be protected. The activities may need to be rescheduled. This is the essence of SIMOPS management. One operation can change the risk profile of another operation. Lesson. Permit interaction must be actively managed throughout the work. Human factors in PTW. 5 scenarios. Production pressure. We've done this before. Shift handover, contractor unfamiliarity, communication failure. Now let us address the human side of permit-to-work systems. Many PTW failures are not caused by complete absence of procedures. They occur because people interact with the system imperfectly. Consider production pressure. We need to finish the day. Consider complacency. We've done this job 50 times. Consider normalization of deviation. We usually don't bother with that step. Consider assumption. Someone else must have isolated it. Consider poor communication. The night shift knew about the change. And consider confirmation bias. We expected the equipment to be isolated, so we interpreted the evidence that way. A mature HSE professional challenges these assumptions, but challenge does not mean confrontation. Instead of saying, "You are wrong," ask, "Show me the isolation." Instead of, You cannot do this. Ask, what has changed from the original risk assessment? Instead of, the permit says it is safe. Ask, what evidence confirms that the controls are actually in place? This creates a verification culture. Shift handover, extension and revalidation. Day shift permit transitions to night shift. Permit continuity is another important control. If work extends beyond the original period, the permit must be managed according to the site's procedure. Do not simply change the date. Consider what changed, who is now responsible. Are the same people working? Are the same controls available? Has the process condition changed? Has weather changed? Are new simultaneous operations underway? Are isolations still valid? Does the work scope remain identical? Does the permit require revalidation? A shift handover must transfer meaningful information, not merely paperwork. HSE PTW guidance specifically identifies shift handover, clear responsibilities, and communication as important features of an effective system. HSE, permit closeout, completed job transition through, inspect, clear, restore, handover, close. Now the job is complete. Is the permit automatically complete? No. Of controls, competence, communication, monitoring, review, and continual improvement. NEBOSH's current general certificate is explicitly focused on the ability to identify and control workplace hazards, carry out risk assessments, and develop practical actions that improve workplace safety. NEBOSH, the PTW system, provides a practical application of those principles in high-risk work. From an IOSH-oriented professional perspective, effective safety management also requires leadership, worker involvement, competence, consultation, and communication. The important point is this: do not study NEBOSH and IOSH concepts only to pass examinations. Apply them. When you review a permit, apply risk assessment principles. When you inspect an isolation, apply verification principles. When you challenge production pressure, apply leadership. When you involve workers in a toolbox talk, apply consultation. When you investigate a permit failure, apply learning and continual improvement. That is how professional HSE competence develops. Field verification, the professional test. HSE officer walking the worksite with clipboard. Checklist appears. Location scope personnel competence isolation gas test barricades fire protection rescue just a method statement toolbox talk maps. Here is a challenge for you. Imagine that a permit is perfect on paper. Every box is completed. Every signature is present. But when you arrive at the worksite, the barricade is missing. The gas detector is not available. The fire extinguisher is absent. The isolation cannot be verified. The crew has not been briefed on a change. And another contractor has started work nearby. Is a permit safe? No. The document may be complete. The work system is not. This is why competent HSE personnel verify conditions at the point of work. Employability and career application. Career pathway. HSE trainee, HSE officer, HSE supervisor, PTW coordinator, HSE lead, manager. Background industries. Oil and gas, LNG, refinery, petrochemical, EPC, construction, shutdown. The knowledge developed in this module has direct relevance to high-risk industries. Oil and gas, petrochemical, LNG, refineries, EPC projects, construction, maintenance, shutdowns and turnarounds, industrial facilities. A professional who understands advanced PTW should be able to contribute to permit review, field verification, high-risk work control, SIMOPS coordination, isolation verification, gas testing control, permit suspension, safe restart, and permit closeout. But there's an important professional distinction. Completing this training does not automatically make a person legally competent, authorized, or appointed to issue permits. Formal authorization depends on organizational requirements, competence assessment, training, experience, applicable legislation, site procedures, and the specific responsibilities assigned by the employer or operating organization. Training provides knowledge. Competence requires demonstrated ability. Authorization is an organizational decision. Never confuse the three. Final module summary. 10 principles appear sequentially with green check marks. Let's summarize Module 10. Number 1. Permit before applicable high-risk work. Number 2. Risk assessment before authorization. Number 3. A permit does not make hazardous work safe by itself. Number 4. Verify the controls at the work site. Number 5. Test the atmosphere where required. Number 6. Confirm isolation and control stored energy. Number 7. Manage permit interaction and SIM-ops. Number 8. Suspend the permit when conditions change. Number 9. Communicate changes to everyone affected. Number 10. Close the permit and restore the work site or plant safely. Remember the complete control philosophy. Plan, authorize, verify, execute, monitor, suspend when necessary, reassess, restart safely, close out. That is professional permit to work management. Closing message. 3 consistent KAYHAB 17 HSE characters standing in front of refinery. Behind them, Module 10 complete. A permit board changes to controlled, verified, safe. KAYHAB 17 logo prominently displayed. Before you leave this module, remember one final principle. A permit to work system is not permission to take risk. It is a disciplined system for controlling risk before, during, and after high-risk work. The strongest HSE professional is not the person who approves the greatest number of permits. It is a person who understands when work can proceed, what conditions must exist, when work must stop, how controls must be verified, and how the operation can safely return to normal. In high-risk industries, professional judgment matters, verification matters, communication matters, leadership matters, and above all, people must never become the control for a hazard that should have been controlled by the system. This is KAYHAB 17 HSE Academy, Module 10, Advanced Permit to Work in High-Risk Operations. Take the knowledge to the field. Question assumptions. Verify controls. Respect the permit. Protect the people. And never confuse production progress with safety performance. Plan the work. Control the risk. Verify the conditions. Execute safely. Close the job properly. This is the standard of professional HSE practice. KAYHAB 17, HSE Excellence in Action. End screen.